We'll continue our discussion of gravitation today, but probably this is the last lesson about gravitation. This I have chosen intentionally because I do not want to start the new lesson because the weekend is coming and I want you to work on this topic on this weekend. So there are just a few questions that I have selected for today's discussion related to the more recent topics that we have covered in gravitation. And after these questions, you should be in a position to attempt the questions that I have shared with you in the worksheet. So I hope you have already started working on the questions related to this topic, and I hope the things have started to make sense now. One question that I have selected for discussion is related to the expression itself, expression in the gravitational potential energy is expressed. For example, they have asked a question to explain how change in gravitational potential energy, which means delta EP, can be expressed as is equal to mgh if height is small for small values of h. That means if you remain close to the surface of the earth, it is correct to express the change in gravitational potential energy as mgh, as you have done in previous classes. Let's see how we can show that. We know that the expression is minus gmm over r. This is the standard expression for gravitational potential energy at any distance r from the center of the earth if mass m is involved, and this is the mass of the earth and g is gravitational constant. If we are initially at the surface of the earth and a mass is lifted through a small height h and carried to a new position which is at a distance r, capital R plus h from the center of the earth, and this was its initial position, which is obviously equal to the radius of the earth. That means if you are initially here, the gravitational potential energy is minus gmm over capital R, and at this position it is minus gmm over capital R plus h. So if I want to see the change, I take the difference of these two and the change becomes this. On simplifying, it becomes gmm taken as common minus 1 over r plus h and plus 1 over r. On further simplifying this expression, it becomes gmm as it is, and this you can take in the denominator, the product I mean, and here it is minus r plus h. So clearly these two R get cancelled and you are left with G M M over R plus H into R, and you have one H here which survives in the denominator. One last assumption that we make in this expression is that this height is very small, so we can ignore it when we add it to the radius of the earth. So R plus H is taken equal to R. With this assumption, it is approximately G M over R square with H here. With this R ignored, R multiplied with this R becomes R square. So we are left with GMM over R square times H. If you recall, this GMM over R square is the gravitational force between the mass and the earth when mass is very, very close to the surface of the earth, almost on the surface. So GMM over R square is nothing but mg. So this all reduces to mgh, and this is what we wanted to prove. This appeared in one of the exam papers, and all this working is for 4 marks. That means you need to understand why this expression that we have defined in this for this topic, and it appears to be very different from MGH. But if we make this assumption and we simplify how this change can be worked out, it reduces to the same familiar expression MGH that we have studied already in previous classes. So this was one question that I chose for discussion. Let's come to another question, and that is related to the escape speed that we discussed yesterday. All planets, all stars, all satellites, they have some gravitational pull to their center. They have certain gravitational value of acceleration, and all objects fall towards their center. Moon is no exception. So if Moon, which is a natural satellite, is having a certain value of gravitational field strength on it, and objects, when allowed to fall freely, they fall towards it. Naturally, we need to throw objects with some speed from its surface if we want them to leave the gravitational pull of the Moon. And for this purpose, there are 2 quantities given, and with those 2 quantities, we can calculate the escape speed from the surface of the Moon. This V escape can be calculated with the help of 2 values given. One is the mass of the Moon, and mass of the Moon is given equal to 7.4 into 10 raised to power 22 kilogram. The second information provided about the Moon is its diameter. Its diameter is given to be 3.5 into 10 raised to power 6 meters. How can we calculate the escape speed with these 2 values given? As we discussed earlier, that we must know what is the gravitational potential energy at the surface of the planet, or the gravitational potential energy at the surface of Moon in this case. And if we know it at the surface of this, and at infinity it is 0, the change in gravitational potential energy will be 0 minus g m over r. This r is radius of the moon. This is the mass of the object we want to throw. This is the mass of the moon, and this is the radius. All this change in gravitational potential energy must be equal to the initial kinetic energy at the surface. So if this is, after simplification, it becomes gmm over r. This must be equal to initial kinetic energy at the surface of the moon. So half mv square must be equated to gmm over r. In escape speed, mass of the object does not matter. As you see, it gets cancelled from the two sides, so it is immaterial what object we are throwing. Escape speed for all objects will be same, whether you are throwing a stone, a cricket ball, or an arrow, or a rocket. For all these objects, the escape speed will remain the same. So if you simplify it further, v is equal to 2 times g m over r under root. And when I use all these values given here, the value of g is given in the data booklet, the value of m is written here, and the value of r can be used here from the value of diameter. So after using all these values in this expression, it is easy to see that it comes out to be 2.4 into 10 to the power 3 meter per second. So this is the escape speed from the surface of the moon. Let's see another such question that is not about the escape speed, but this is also a certain speed acquired by an object when it falls freely towards the earth. At a certain distance, the speed it has already acquired can be calculated using similar ideas. For example, if this is earth and an object is falling towards it from infinity, it's initially at a very, very large distance from it. Suppose this is the distance we call infinity. It starts falling freely towards the earth, and at certain distance, which can be expressed in terms of radius of the earth, it is 1 r from the surface, it is 2 r from the surface, and it is 3 r from the surface. 3 times the radius from the surface. So this is the point at which we want to calculate the speed that the object has acquired before it falls further towards the earth. And of course, the assumption is that all the potential energy that decreases in this process is equal to kinetic energy, and there are no dissipation of energies involved here. We want to calculate what is the speed here at this position, and this position is 3 times the radius of the earth if the object falls from infinity towards the earth. So a similar idea can be used here. The idea is, since the object has started from infinity, it is the zero potential energy there. and if it falls to this position, it has a certain gravitational potential energy here. The gravitational potential energy at this position is minus g m m over 4 times the radius, because the total distance from the center of the earth is 4 times the radius of the earth. So in the expression for potential energy, we use 4r and not 3r. 3r is from the surface. If we want to calculate the change in gravitational potential energy, is obviously 0 minus g mm over 4r. So change is g mm over 4r. But all this change, which is actually a decrease, if you choose to take this minus 0, it appears negative, but in either case, you ignore the sign and you just take the magnitude of that change and equate it to the kinetic energy there. So all this loss in potential energy must correspond to the gain in kinetic energy. So in a very, very simple way, you can calculate the speed that the object must acquire after it has lost a certain gravitational potential energy, starting from infinity to a certain point where the gravitational potential energy is smaller than 0, and therefore it has lost its value, and that lost in potential energy must correspond to some gain in kinetic energy. M gets cancelled from the two sides again, and on simplifying it, it is easy to see that V is g m over 2 times the radius of the earth and under root. So this is the speed that the object will acquire. If I know the mass of the earth, which is a commonly known number usually given in the statement of the question, and I know the radius of the earth, I use these values to calculate that speed. I have given you this type of question in one of the assignment I have shared with you. So with this question discussed, you should be in a position to attempt that question on your own now without any problem. Another question that I would like to discuss is a question that I also discussed earlier in some detail, but I feel I can add a few things to that discussion as well. So let's discuss that as well. In this question, we will consider two stars. One star is labeled A, and the other star, which is at a very large distance from it, it is relatively smaller in size, and the two stars are at a distance. Let's say we know this distance 1.4 into 10 is power 12 meter from the surface of the other star. This is star B. The problem is that we want to throw something from the surface of this planet with a certain speed, with a certain kinetic energy, so it reaches this surface easily. It doesn't stop in the midway. So in order to do this, we must understand the kind of information we have been provided. The information provided for this purpose is the variation in gravitational potential as we move from this position, which is given in terms of the values of x here. And let's quickly write these values here first, and then we'll discuss what they are saying. This is 0.2 times 10 raised to the power 12 meter. This is 0.4, 0.6, 0.8, and this is 1, and then this is 1.2. This is actually the total distance between the two. At 1.2, starting from here, we actually start from this to reach the surface of this planet. Another set of values which appear on this side of the graph, they are -2, -4, -6, and they are the values of potential with this factor 10 raised to the power 8 joule per kg, and these values are like -8, -10, -12, and -14. So if they show you how these values of the potential change with distance, this is the kind of curve they have shown. The curve continues and it falls to this level at this position. So this is how the variation is given. I discussed this variation in the last lesson, but let's see what could be added to this discussion. There were two quantities they have asked you to calculate. Number one, they might ask you to calculate the change in kinetic energy when you throw an object from the surface of this planet so it reaches this planet. The total change in kinetic energy is obviously equal to the total change in potential energy, the gravitational potential energy. An object which is initially at this position, which is 0.1 into 10 raised to the power 12 meter, which is the surface of this planet, and we have this value of gravitational potential energy here, which is -10 times 10 raised to the power 8 joule per kilogram. If we throw an object from here, its gravitational potential energy goes on increasing until it becomes maximum, and then it goes on decreasing. This curve depicts the change in gravitational potential energy. So the maximum change, if we see carefully, is the gravitational potential energy. The total change from this position to the final position is actually between these two values, this and this, because the object starts here and the curve continues like this, and this is the final value of the gravitational potential energy when the object reaches this planet. So the total change in gravitational potential energy is actually the initial value of gravitational potential energy and the final, which is -14 times 10 raised to the power 8. So total change in kinetic energy, which is equal to the change in potential energy basically, that is 14, that is m times 14 minus 10 into 10 raised to the power 8. This mass appears here because the change in potential is provided in the question, but until you multiply it by mass, you cannot make it energy. So in order to make it the change in potential energy, we multiply it by the mass. And if mass is given to be 180 kilogram of that object, which may be a rocket or something, it is 180 times 14 minus 10, which is 4 into 10 is power 8. And if we simplify it, it obviously becomes 7.2 into 10 is power. This is something I did earlier. The change in kinetic energy is equal to the change in potential energy. And since we have the change in potential already from the graph, which is between these two values, the initial value and the final value, so we can quickly change the calculate the change in kinetic energy. Now, what should be the minimum speed with which we can throw an object from this position so it reaches here? And for that purpose, we need to understand that we have to overcome, it is now an idea like escape speed, you must overcome this barrier. This is the total change in gravitational potential energy that you have to overcome so the object is able to continue its motion on its own after it reaches this position. So you have to throw it with a certain speed so it reaches this height. It's approximately 0.5 into 10 to the power 12 meter, and after it reaches that height, maybe here is that height, and after it reaches here, it will come under the influence of the gravitational pull of this planet. So it will continue on its own and will keep falling towards it. So if we are required to calculate the minimum speed with which to throw an object so it reaches this surface, we have to consider the change between this and this value. So this time, if I want to calculate the minimum speed, so the mass reaches the surface of star B. If you are starting here, what is this minimum speed? So the mass reaches the surface of star B. So in order to calculate this, you have to write the total, the initial kinetic energy at this surface, that must be equal to total change between these 2 points now. These are the points where you will consider the values of the potential. So this time mass into, this time you will minus 4, this is probably 4.2 or 4.3 from this graph. So let's say it is 4.2. So 10 minus 4.2 into 10 is power 8. And this is the equation that will give us that speed. So m will get cancelled from the two sides. And after you simplify it, this is probably close to 3 into 10 is power 4 meter per second. So this is the minimum speed with which you throw an object of given mass from this surface of this star, and ultimately it will reach here. So all these questions that we have discussed in the later part of today's discussion deal with the same simple idea of conservation of energy. You just have to understand which values are to be used to calculate the change in potential energy, and then equate it to the kinetic energy to calculate the change in kinetic energy or the speed that it acquires ultimately. So I hope these questions will be helpful in attempting the worksheet that I have shared with you all, and to attempt many more questions of a similar type. Next week we'll start the new topic, that is oscillations. Thank you.